who's at CNRS, and he will talk about barcodes and Hamiltonian homomorphisms.
Back to life? Yeah. Okay, so we have a symplectic manifold, and ham of m, as usual, denotes Hamiltonian diffeos for me. And what I'm really interested in studying or addressing in this talk, or if you guys could see this corner, is what I denote by ham bar of m. So this is the set of Hamiltonian homomorphisms of our symplectic manifold. And so these are, by definition, what you get in the C0 closure of ham, taken inside the group of homeomorphisms of M, in homeo of M. Okay? So these are those homeomorphisms which arise as C0 limits of Hamiltonian diffeomorphisms. And one of the main goals of C0 symplectic topology is to study these guys. However, one of the difficulties we have in the field is kind of a lack of tools. So for example, floor homology or Hamiltonian floor homology is defined for smooth objects, and it's not at all clear how you write down Floor's equation for a homeomorphism. And what I want to explain to you today is that via the theory of barcodes and persistence homology, there is an indirect way of defining floor homology for homeomorphisms, and then I'll show you how this is done, and then I'll give you some applications towards in the second half of the talk, hopefully. Okay, so let's start with barcodes. So can people see this side? Since I got, okay. Maybe you cannot see there. So okay, I'll avoid this thing. So barcodes. Let me give you the definition. So I'll begin with what I call a finite barcode, as opposed to a barcode, which might be infinite for me. And then we'll move on to infinite barcodes in a few minutes. So by a finite barcode, I mean a finite collection of intervals of the form. So here's what a barcode looks like to me. So let's call the barcode, say it's B. It's a collection of intervals, so I sub j. Now the same interval might appear several times. So intervals with multiplicity. So I put ij, comma mj. Now the interval can be of two forms: a finite closed interval, or it could be a half-infinite interval. Okay, and so mj is, as I said, it's a multiplicity, so it's a natural number. Okay? So that's what a barcode is. If you want to see a picture, maybe I'll draw a picture here. I mean, I'll think of the real line as this vertical direction, and it's just really, it looks like a barcode that you see in a grocery store. So here's same bar appearing twice, another finite bar, except these half-infinite bars, they don't appear in a grocery store. What's that? I can't hear you. Hey, I mean, when they scan all the grocery stores actually have barcodes. Okay, great. So, I mean, maybe those ones are a little more complicated than the ones I study. But, okay, I mean, I think that's where the name comes from. That's why the people who invented barcodes decided to call them barcodes. Now, so the space of barcodes can be equipped with a distance called the bottleneck distance. And so this is kind of a fantastic idea. that allows you to make measurements. And I want to tell you what the bottleneck distance is. Okay, so suppose you have two finite barcodes, let's say B1 and B2. And I'll tell you what the bottleneck distance between the two is. So first we'll say B1 and B2 are delta matched. Okay, so eventually when I define the distance, being delta matched will imply that their distance, their bottleneck distance, is less than delta. If the following happens, up to adding or deleting small bars of length less than 2 delta. So up to ignoring short bars, you can find a bijection. So there exists a bijection I'll call phi from B1 to B2. So this is 1-to-1 and onto map such that the matched bars are, the matched intervals are close to each other. So the endpoints of I, so say I is in B1, and then phi of I will be the bar that's matched to it in B2. So the endpoints of these two intervals are within delta of each other. Okay, so let me draw a picture. You see this is quite a natural notion. So here's, maybe I'll do blue and pink. So here's, say, B1. And I'll draw the B2 in pink bars. So let's say in B1 you've got, I don't know, 2 bars. Maybe I'll draw them equal length. Another bar like this. So the horizontal placement of the bars doesn't really matter, but I got to draw them somewhere on the board. Maybe you've got a bunch of short bars that don't really matter because you're going to ignore them. And then let's put a half infinite bar too. Okay, so if B2, so I'm going to draw B2 such that it's delta matched with B1. That means for each one of these long bars, I need to find a long bar, I need to draw a long red bar whose endpoints are within delta. So there could be one here. There's got to be one here, and this distance has to be less than delta. So this is less than delta. And this distance is also less than delta. I need another one here, so it could be like this. Again, shorter than delta. Another one over here. And then I need one half infinite bar here, whose endpoint, again, has to be within delta of the endpoint of the other bar. Okay? So it's quite a natural notion, easy to understand. And then, as I said, this implies once barcodes are delta matched, eventually will imply that the bottleneck distance is less than delta. So you could probably guess what the definition of the bottleneck distance is. Then you define the bottleneck distance between B1 and B2 to be the infimum of deltas such that B1 and B2 are delta matched. Okay, so that's what the bottleneck distance. And this turns the space of barcodes into a metric space. Now these notions, so again, recall here I ignore the short bars. So the red bars could have a gazillion bars length shorter than 2 delta, and that would not affect being delta matched. Yes? I'm sorry? Yes? So I could have, as I was just saying, the red one could have 1,000 short bars, and they don't need to have anything to do with these short bars. Okay? So these notions, so barcodes and bottleneck distance, they appeared first in the field of topological data analysis. And maybe the names I should cite here. So there's a lot of names, and I don't really know all the literature too well. I'll say the names and I'll write the initials. So the names that are often associated with this notions are Edelsbrunner and Herrer. There's also papers by Carlson and Zomorodian. And also there is Chazal, Cohensteiner, so Chazal, Cohensteiner, Gliss, Guibas, and Udo, GGO. Okay, I think there are many, many, many other people. I'm not too familiar with the topological data analysis picture, but in symplectic topology, so these notions were introduced to our field in a very nice paper by Polterovich and Shulukhin back in, I think, 2014 or 15. And ever since then, they've had many, many, many interesting applications in our field. Now, so before I get into symplectic topology, I want to show you how barcodes arise in Morse theory. And I'll do this by telling you how one can associate a barcode to a Morse function. Okay, so suppose you have a Morse function on your favorite manifold. So it's Morse and has, so I'll need, for this part, I'll need to assume it has distinct critical values. You could kind of ignore that for now. So, I don't know, I think that's called a very nice Morse function or something in the literature. Perfect. And I'll show you how to associate to this a barcode, so, which I'll denote by BF. And we'll do this by considering the homologies of sublevel sets of the function. Okay? So every time, this is what's called a persistence module, and every time you've got a persistence module, and I'm not going to define persistence modules, you could associate to it a barcode. I'll do this for a Morse function. So what I'll explain is due to Baranikov, although he doesn't use this language. And the specific procedure I'll use is from a paper by Le Potrec, Nier, and Viterbo. So I think this is from 2011, and this is maybe 2002 or something, 2005, I can't remember. But this is before barcodes even existed, but this was there. So it's kind of there in his paper, but it doesn't use the language of barcodes. And the barcode, one feature of the barcode will be, so I want you to keep this in mind, the endpoints of this barcode will be exactly the critical values of my Morse function. Okay? So let's draw a simple enough function on the sphere. And I'll draw for you the barcode of this function. So here's f, here's the real line. Maybe I'll call this A, B, C, D. This is the max, and this is the min. And I'll show you what the barcode for this function is. I'll tell you, give you an idea of how you'd construct a barcode for this guy. So, as I said, the endpoints of the endpoints of the barcode will be the critical values of the function. So each critical value will be the endpoint of some barcode, some bar. And I'll tell you how to find a bar whose endpoint sits at A. So what you do is you look at a small window around the value A. Okay? So A, I'll use it to denote both the critical value and the critical point. And you take this, so say this is a window of, I don't know, length 2 epsilon. So I'm looking at this homology group. And then I want you, so this, at this point, it's just, there's just one value here. So this is just Z2. It's got one generator. Now you take the upper edge of this window and shift it up. So shift it up to, say, lambda. And while lambda sits below the value B, nothing happens. This just remains Z2. That the point A keeps on generating this homology group. Okay, and as soon as you pass the value B, so what happens is something happens as soon as you go past B. And at that point, the homology class which was generated by A all of a sudden dies because it comes to the boundary of B. Okay? So this says, once this happens, then I know I need to draw a bar that starts at A and ends at B. So maybe I'll say more formally what happened here. So what I did was I looked at the inclusion, this inclusion. So that corresponds to raising the upper edge of the window. And you could see that this I lambda, this inclusion map, the map induced by the inclusion, becomes 0 if lambda is sufficiently large. And the first time it becomes 0 is at the value B. So B is the infimum of lambda such that I lambda is 0. Okay? So there's two pieces of data that I communicated to you here. First says that A is the lower end of a bar, and the second one says that the upper end of the bar is B. The fact that A is the lower end point of a bar comes from here. So this says that I've got a bar that looks like this. And the fact that this bar terminates at B comes from this second thing that I wrote here. So this tells you that I've got a bar like this. Okay? So this condition is in the paper of Le Potrec, Nier, and Viterbo. They call these kinds of critical points as lower critical points. Lower means that I lambda becomes 0 once you raise the upper edge. Okay? And then it could be that, so there's another form of critical point, which is the upper critical points. That's like B, if they happen to be the upper end of the bar. And so I'll explain what happens by drawing the one for, so there's going to be another bar that goes from C to D. So I'll draw this one here. So there's going to be another bar that goes from C to D, and if you start the procedure that I explained before at C, you get the exact same picture. But maybe you start at D, and you want to see what happens then. So what you'd have to do then is look at this map, kind of the dual. So you look at the inclusion of, so what you do is you go to D, you look at this homology in this window, and then you lower this edge of the window and see what happens. And wait till the homology class represented by D dies, or maybe stops being a homology class, stops being a cycle. So that corresponds to the following map. Maybe I should write a little lower. Well, and so you see what happens is that as you decrease lambda, eventually this map becomes 0. So I lambda is 0 for lambda very small. This tells me that, so I'll continue this here. This tells me that I've got a bar that looks like this. Its upper edge is upper end at D, and then it will terminate somewhere, and that's going to be C, because C is the supremum of such values. Okay? And these are what in this paper are called upper critical points, or upper critical values corresponding to upper and the upper end of a bar. Yes?
Do you look at homology and the degree of the index of the point? Or?
Yeah, well, I mean, if you don't look at homology and the degree of the index of the point, you'll just have 0. So it doesn't really matter if. When I write H here, I mean, just look at all of homology. But basically, you just need to look at the index, the homology in that degree. Otherwise, you won't see anything interesting. 94? Oh, my. This one is 2011 or 2009, maybe. I can't remember. Okay.
So do you consider the barcode for the whole function f, not for each level set?
Yeah. I haven't finished telling you what the barcode of f is. So these are, here I told you the bars that are finite, but there's going to be some infinite bars. And those are the ones that correspond to critical values or critical points that give you the homology of the manifold. So I guess I'm drawing S2 here, the sphere. Could be the circle anyway, either one. And those 2 points are these guys. So these 2 guys give you the max and the minimum, give you half-infinite bars. So you have half-infinite bars sitting there. And the reason those are called, so those are called homological critical values. And the definition of homological is that it's neither lower nor upper. Now, if you look at a window around here and try to see if it's a lower critical point, you'll see that I lambda never becomes 0 as you raise the upper edge. So you know it's not lower. If you take the lower edge of this window and lower it to see if it's an upper critical point, you'll see that I lambda never becomes 0. So it's neither a lower critical point nor an upper critical point, and that's what you call a homological critical point. So neither upper nor lower. And so this algorithm that I just described gives you the barcode. And the proof that this gives you the barcode, or it's well defined, is written in this paper. So there's a theorem in the paper, maybe I'll just state it, is that they show in that paper, so that's Le Potrec, Nier, and Viterbo, that this decomposition into lower, upper, and homological is really a decomposition of the critical values. This union is a disjoint union, and it gives you all critical values. So that tells you that this is a well-defined procedure.
So then what if the maximum is the same several times?
You mean several local maxima?
Yeah.
First I assumed that the critical values are distinct. So there's only one absolute maximum. Okay? The other local maxima will all be upper ends of bars, finite bars. So if you're looking at the circle or the sphere, you'll only have 2 half-infinite bars because homology has got rank 2. The number of half-infinite bars is the rank of the homology of the manifold. Okay? So there was something else I wanted to say. Yeah, so the barcode of a function encodes quite a bit of information about the homology of the sublevel sets. Yes?
In your definition, you have this MJ.
MJ is the multiplicity. Multiplicity of IJ. So it's because a barcode, I allow a single interval to appear twice, as I drew it, for example, here. Okay? In this setting, for this Morse function, this doesn't happen because it has distinct critical values. So the barcode, so maybe I'll draw that barcode. The barcode, if you were to draw it here, it looks like this barcode. So A, B, there's CD here, and there is M, and there's another one down here at little m. And that's the barcode of this Morse function. Now, as I was saying, one can show that the barcode encodes a lot of information. So for one thing I'll tell you is that if you have 2 functions such that the barcode of f is equal to the barcode of g, then, for example, it tells you that the homology of sublevel sets of f equals the homology of sublevel sets of g for all t. It actually encodes more information than that. Okay? It's actually just a combinatorial way of keeping track of all the kind of information that's contained in the homologies of sublevel sets of F. Now, an interesting feature of barcodes for Morse functions, here's a fact, is that the bottleneck distance, and this is where you see things starting to get how we're going to go from Morse functions with distinct critical values to functions that are less regular. You see that the bottleneck distance, one can show that the bottleneck distance can be bounded by the sup norm. Okay? So it's not very hard to prove, but maybe it's not obvious if you're not familiar with these notions. And this allows me to, so for example, one implication here is if I make a C0 small perturbation of my function, then the barcode is going to change by a small amount in the bottleneck distance. So if I do this, so let's say I add a zigzag here, and I add this. So this is a C-infinity large perturbation, but a C0 small perturbation. And since I know that the barcode cannot change by much, then I know the new barcode will just have this tiny bar introduced over here.
If I take the circle and just throw it back the way it started, right? So there's only two digits.
Yeah?
The barcode would be just two digits.
Exactly. Yeah.
If I take a sphere, it will also be two digits.
Exactly. So the number of rays is just the rank of the homology.
So the barcodes are the same in this case.
Well, the barcode, you mean for the sphere? Well, kind of. There are two rays, but the barcode contains more data than the number of rays. It's also the starting point of the rays. So if, yeah, then it will be the same.
But the homology of the sub-level sets is not the same.
Well, I'm assuming here is on the same manifold. Okay. Sorry.
So, Renato, why do you introduce a new little piece for the barcode and you don't have like two barcodes that go like this?
Yeah, so you mean why doesn't it go like from here to here? And,
Why don't you split that bar and have them overlapping a little bit?
well, so one thing is you could work out this algorithm and you'll see that it doesn't give you that. Second thing is that by this fact that I just stated, I introduced a small bar, right? The new barcode must be close in bottleneck distance to the old barcode. And the only way it will be close is by introducing this tiny bar here. If you split it up, the distance in bottleneck distance will be large. Okay.
I guess I don't understand the difference between lower and upper. Like the distance between the left side and the right side of the sphere.
So I'm not
Why
sure.
is AB lower and DC upper?
No, look, AB is not lower. A is a lower point, C is a lower point, B is an upper point, D is an upper point. Lower is a critical value is either lower or upper. Okay, not a bar. Okay. Okay, so now this inequality is important to me because look at what I could do with it. Now I take your function, so this is where you see C0 stuff coming. Take your function that's C0, not even smooth. And I can define a barcode for it. So I define the barcode of f to be the limit of barcodes of fi, where fi's are, so fi is Morse, fi Morse with distinct critical values, and fi converges in soup norm or in C0 topology to f. Okay? Now, this inequality tells me that this so the fact that this is the bottleneck distance bounded by the soup norm tells me that this sequence is Cauchy. So it has a limit in the completion. So BF actually is not going to be a finite barcode anymore, but it's going to be, it's going to live in the completion of the space of barcodes or finite barcodes. And this completion is not some abstract space. You could actually represent it. You could actually give a very nice description of it, which I will do now. So that's what I call the space of barcodes rather than finite barcodes. So this BF that for a C0 function, BF lives in the space of barcodes as opposed to finite barcodes. And this consists of a bar in here is of the following form. A barcode in there is of the following form. You have, again, intervals with multiplicities. Now the number of intervals could be infinite, but they must satisfy the following finiteness condition. For any given epsilon, the number of bars whose length is greater than epsilon must be finite. Okay? So you could have infinitely many bars, but they all have to be very short. And the way this arises is quite easy to see why this happens. is, for example, just take a piece of that picture. Suppose I have a picture like this. This is from some Morse function in the circle or in the sphere. And here I have a bar, let's say like this. And now I make a C0 perturbation, and I introduce a lot of zigzags like this, which accumulate at this critical point. And what the effect of that would be is for each one of these zigzags, I will have to introduce a short bar. And you could see that you'll get a ton of short bars, which are getting shorter and shorter and accumulating at this critical value. So you get a picture like this. Okay? So that's how the barcodes for C0 functions are different than barcodes for smooth Morse functions. Okay, so I'm done with the introduction to barcodes. Now we can move on to symplectic topology. Okay, so for the rest of the talk, I'll have a closed symplectic manifold, and I'll assume it's aspherical. So pi 2 is 0, or omega vanishes on pi 2, and C1 vanishes on pi 2. And now suppose you have a Hamiltonian. So you could start with a non-degenerate Hamiltonian on the manifold. Then you could associate it, as we all know, via Hamiltonian floor theory, the filtered floor homology groups of H. And then, just as I did, is literally no different, maybe small differences, than the Morse setting. You could pass from here and construct a barcode B, which I'll denote by B of H. So this is explained very clearly in that paper of Poltrovich and Shaluchin that I mentioned. Okay, so I won't say anything about filtered floor homology, except I'll say it allows you to associate a barcode to every Hamiltonian. And these barcodes have the following feature. So the bottleneck distance between, say, barcode of H and the barcode of G is bounded by the Hofer norm of H minus G. Okay? I actually won't use this feature, so I won't define the Hofer norm or if you want, I could do it. But so let me draw what a barcode looks like for a Hamiltonian. It's not that different. Could have small differences in the Morse barcodes, but maybe I'll draw one so that I could introduce some more notation. So suppose a barcode for a Hamiltonian could look like this. You could have a bunch of finite barcodes, finite bars, which I'll draw here, and then you'll have a number of half-infinite bars. So maybe I'll draw one more here. Okay, and as in the Morse case, the number of these ones, the half-infinite ones, is equal to rank of floor homology of M, which is the same as rank of singular homology of M. Okay, so the lowest of these endpoints corresponds to the homology, the level in filtered homology where you see the floor homology class of the point. And the biggest of them corresponds to the level where you see the floor homology class of M. And the other endpoints in between are the values of what are called the spectral invariants of the Hamiltonian. Okay? So this is, the smallest and the biggest are the ones that have most applications in symplectic topology. So this is usually called C plus of H. And this one is usually called C minus of H. So these are the spectral invariants that were introduced by Viterbo and maybe in this setting by Schwarz. And the distance, so the difference between the two, so this distance, so this is called gamma of H, so it's by definition C plus of H minus C minus of H is the so-called spectral norm. Okay, now I want to go from Hamiltonians to Hamiltonian diffeomorphisms. And for this, we'll use the following fact. Suppose you have two Hamiltonians that give you the same diffeomorphism. Yes, the vertical action. Yeah, thanks for pointing that out. So these are action values at which you see these homology classes. Okay, so suppose you have two Hamiltonians that give you the same diffeomorphism. Then, by a theorem that's due to Seidel and Schwarz, you know that the barcode of H will be related to the barcode of G by shift by a constant. This is because you could show, so using their theorem, you could show that the following is true. The filtered floor homology of H is the same as the filtered floor homology of G up to a shift by a constant. I think I need to put the C here if I want to write it that way. Okay? So look at what this tells me. So then I get a mapping from the space of Hamiltonian diffeomorphisms to the space of barcodes, but modded out by shift, quotiented out by shift. So this is up to shift. Okay? So this is how you associate a barcode up to shift to a Hamiltonian diffeomorphism. And now, finally, I could tell you, if there are no questions, I could tell you what how the main theorem of the talk is, which allows us to define barcodes for homeomorphisms. So here's the theorem. I'll say afterwards who proved it, or if it was proven in several stages, so I'll just say it afterwards. So consider, so I think of ham of m, as I just said, I have this mapping which I call, B from ham of m to the space of barcodes up to shift. Okay. Now, I equip ham of m with the C0 topology. So the topology induced by C0 distance, topology of uniform convergence. And I equip the space of barcodes up to shift with the bottleneck distance. So the bottleneck distance descends to the quotient. And now I have a mapping of two metric spaces. Okay? And the theorem is that this mapping is continuous. Is continuous. And moreover, it extends to the closure. To what I called Hamiltonian homeomorphisms. Okay? So what I get here is that, in fact, I have a mapping defined from the space of Hamiltonian homeomorphisms to the space of barcodes. Okay? So what this says is, if you want to think about it, is, so what the theorem was saying is, you take a Hamiltonian diffeomorphism, you make a C0 small perturbation of the diffeomorphism. So that's quite different than saying make a C0 small perturbation of the Hamiltonian. And then the barcode just changes by a small amount. Okay? So the fact that if you make a C0 small perturbation of the Hamiltonian and the barcode changes by a small amount, that's quite easy. That's the immediate consequence of this. But the fact that if you change the Hamiltonian diffeomorphism by a C0 small amount, then the barcode changes by a small amount is a consequence of this theorem. I mean, it's exactly what this theorem says. And not only that, you have some control. The map is somehow locally uniformly continuous, so you could extend it to the closure. You have enough control to extend the map to the closure. And so this is what I meant when I said that we can indirectly define Hamiltonian floor homology for homeomorphisms. And then I'll tell you what some applications of this are. So this theorem was proven, as I said, in several stages. In the dimension, on surfaces, this was proven in a paper by Frédéric Leroux, myself, and Viterbo just a couple of years ago. I can't remember the year now. And then then there was another proof. So when the dimension is, I mean, what was new was for the case of 4, but the proof that we gave afterwards works in dimension 2 as well. And this appeared in a paper of by Bohovsky, Humilier, and myself. And that's from 2018. I think this paper also appeared in 2018, but somehow the results were announced a couple of years before that. And maybe I'll say a word on the proof here, and that's all I'll say about the proof. It's got 2 steps. So the first step is that first, one shows that the bottleneck distance between, say, you've got F and G, 2 Hamiltonian diffeomorphisms, it can be bounded by gamma of F inverse G, where gamma is this thing. So maybe I didn't say something here. See, gamma is defined for the Hamiltonian, but as I said, the barcode doesn't depend on the barcode up to shift doesn't depend on the Hamiltonian. So since this is a difference of 2 spectral values, actually this gamma is a mapping from Ham. It descends to Ham. This is the so-called Viterbo distance or the spectral distance or the gamma distance. So you could show that you have this inequality. This is due to Kislev and Shilukhin. And then once you have this inequality, to get the other result, you just have to show that, prove that gamma is C0 continuous and extends to the closure. And that's what we proved. So step 2 is gamma is C0 continuous and extends to the closure. So that's all I'll say about the proof. There has been some progress since our work appeared. So namely on C0 continuity of gamma. So as I said, this was for aspherical manifolds, but my conjecture is that you could prove gamma should be C0 continuous on all symplectic manifolds, but we don't know how to do it yet.
So that's the same side of the element.
Right. This is, yeah, this fact you mean?
That's pi to this is
This is the fact that the Seidel representation is trivial here.
Is there a way to, when it's not true, is there a way to refine this approximation? This operation?
Yeah, it's just, it becomes less obvious than here, but actually I think the barcode, it's still there. The barcode actually doesn't depend on the Hamiltonian. I don't know if it's written anywhere. Yeah, the effect of, when you compose with a loop, so the difference between 2 is that you could go from one to the other with a loop. The Seidel representation tells you how the floor homology changes. But I think what happens, I've never really sat down to prove it, but I think this is true, is it just, the barcode stays the same up to the endpoints, but just the labeling on the bars changes. I mean, the barcode is much more complicated. It's infinite at that point. There are infinitely many infinite bars, half-infinite bars, because of Novikov coefficients. But in the end, if you forget the labels, which is kind of what I'm doing here, if you don't label them with homology classes, then the barcode stays the same. But somebody, I think, needs to prove that, but it's probably, I don't know if that's written anywhere.
It is.
Oh, it is? Where is it written? Oh, okay, great. Okay. I need to look in there. Okay, so actually then barcode map is well defined. Yes?
So are the spectral invariants zero continuous up to this constant? Does that make
Yeah. The difference between, so what this says is that the difference between 2 spectral invariants is C0 continuous.
But
That's the best.
them individually.
It's not.
Even if you take into account even if you kind of mod out by the constant.
Then if you take an individual spectral invariant and mod by shift, then it doesn't make sense. What makes sense? Only the difference between 2 spectral invariants. What makes up to shift, the barcode makes sense. But once you have just a single bar, up to shift, it just doesn't make sense.
Yeah, but I guess the question is, so is it important that you're taking the biggest and the smallest, or if you take the difference between any two spectral?
The difference between any 2 turns out to be C0 continuous, because you could bound it by the difference between any 2 spectral invariants turns out to be C0 continuous. And you brought up a good point. So this shift is absolutely necessary. Without the shift, the theorem is just false. Okay. Any other questions? Oh yeah, you're right. I don't think I've given a talk in which I didn't mess up cytosine, but this is, okay, if I screwed myself over, it's not a big deal. This was proven first on surfaces by myself, so. But I was, okay, so if dimension of M is 2, that was done by myself in my PhD thesis, so 2013, and then dimension of M greater than 2, that's what we did in this BHS. And I was saying C0 continuity of gamma, it's been proven now on CPN by Egor. And after a few months after Egor, a new proof was given for CPN and negative monotone by Kawamoto, who is this joint student of mine and Claude Viterbo. Okay. Any questions? So now I want to give you applications. Now we've got floor homology. What are we going to do with it? So wait a second. How much time do I have? Okay. So maybe I'll start with application 2. And then we'll do application 1. Both of them are fairly short. So application 2, which is now application 1, is to C0 version of the Arnold conjecture. So we all know what the Arnold conjecture says. The number of fixed points of a Hamiltonian diffeomorphism F is at least, is bounded from, I mean, there are many versions, but the version that's suitable for me is this one. It's bounded by 1 plus the cup length of the manifold M. Okay, so one C0 interpretation would be this. The same thing holds for all homeomorphisms. Okay, and so this was studied in the surface dynamics community, and in fact was proven to be true by Matsumoto. There are other proofs of it. He's the first guy to have proven it. There's a really, really beautiful proof by Le Calvez, and also there are proofs by Franks and others. Which says C0 Arnold is true on surfaces. If dimension of M equals 2. And so the number is 1 plus cup length is 2 for the sphere and 3 for the other surfaces. Okay? Now for in higher dimensions, however, we constructed a counterexample. So this is again with Bohovsky and Humilier. We show that if the dimension of M is bigger than 4, or is at least 4, then you can always find a homeomorphism with just one fixed point. It's exactly 1. Okay, so the conjecture, so the C0 version, if you just want to count fixed points, then it's just far from true. It's about as far as it could get from true. And maybe an observation should be that one could show that there has to be at least one fixed point. There's always one fixed point for a Hamiltonian homeomorphism, but you could not do better than 1. Okay, so the conjecture is false, and so we decided to change the statement to make it true. And not in a trivial way by saying that changing this by just 1, but in a slightly more complicated way. And so here is the idea for rescuing the Arnold conjecture. So the idea is count the number of, so it's actually, I can make it more precise, but since there's no time, I won't go in there. Count the number of distinct elements in the endpoints of the bars. So the number of the distinct endpoints of B of F. So what I mean by distinct is here. Suppose the barcode looks like this. There's going to be at least 2 like this. Then I see 1, 2, 3, 4. Okay, not 5, not 6. Okay, so I see 4 distinct elements in there. And what I want you to keep in mind is that, so recall, if you have a Hamiltonian diffeomorphism, then these endpoints are actions of critical points of the action function. So they are actions of one periodic orbits, actions of fixed points. So the number of endpoints is actually a lower bound for the number of fixed points. But of course, this could be very small. So for example, if F, so it's not always good. It doesn't always recover the Arnold conjecture. If F is identity, then all fixed points have the same action. So the number of endpoints is just 1. Okay? But then, so if you count the number of endpoints, you don't get the right bound. But then in this case, it has infinitely many fixed points. And this dichotomy, which is true in the smooth setting, turns out to be true in the C0 settings as well. So the theorem is the following. I'm sorry? Because it's up to shift, you're saying?
No. I'm saying that for identity, with multiplicity, it would be dimension homology, but without it would be 1.
Yeah, so as I said, I mean, that's what I was explaining here. I just count, you take the number of endpoints, write them in a set, and you just count how many elements that set has. So that's why exactly I drew this thing, where you have 2 bars of with the same endpoints. And I say, these 2 different bars, they have 4 endpoints, but to my count, they contribute only 2. Okay? So for the identity, you have the barcode of the identity looks like this. I mean, here is 0, and it looks like this. And where the number is the total number of, the rank of homology. And I see only 1 value here. Okay? But the number of fixed points, as I said, is infinite. So here's the theorem. Again, with BHS, with Bohavsky and Humilier. And what we showed is that, so take a Hamiltonian homeomorphism, and let's count the number of endpoints in the barcode of F. I mean, the barcode is only defined up to shift, but this number of endpoints is independent of shift. So it makes sense. If number of endpoints, so you count the number of endpoints. If that gives you the lower bound for Arnold, we say we're happy. If that violates the lower bound, so if this is less than 1 plus cup length of M, then we can show that the number of fixed points of F is actually infinity. Okay? Actually, we could show quite a bit more than that. We could show the fixed point set is very large. In fact, it has homology. And this is kind of a typical sort of thing once you use techniques from Luster-Schnirelmann theory. You detect homology of the fixed point set. So the statement could be made more precise than that. And so, look, the corollary is this kind of deformed version of the Arnold conjecture. I mean, you could cook up any sort of many statements, but for example, the following is true. If you take the maximum of fixed points of F and number of endpoints, then you cover the Arnold conjecture. Okay, so this statement that I put up here, if you remove homeomorphisms, for diffeomorphisms, it was already known, and it was proven by Wyatt Howard, who was a student of Victor Ginsburg. Okay, and our proof is, it takes his proof and adapts it to the C0 setting. I don't know. I don't think so. I mean, I forgot what was known to Floor. No, not in this form. Not in this form. I assume in the smooth setting it was kind of known to the experts, but maybe it was known, it was not known. But the first place, the only paper I saw where this statement appears, he doesn't count number of endpoints, he counts number of spectral invariants and so on, is in this paper of Howard. Okay. And there is kind of a non-trivial trick in there. The argument's not that difficult, but it is tricky. There's a trick in there that's, it's not obvious. Once you see the trick, it becomes kind of easy, but without the trick, it's kind of looks hard. Okay, so that's application 1, and application 2. Okay. So I've got 4 minutes. Maybe I could give you a deformed version of application 2. So another application of dynamics. Okay, I'll erase this. So I'll go over this rather fast. So this is the notion of Rochlin groups, something that comes from ergodic theory. So suppose you have a topological group G. So G, a topological group. G is said to be, is called Rochlin, or said to have the Rochlin property if it possesses a dense conjugacy class. If there exists, so say, theta in G, such that the conjugacy class of theta, so this is psi theta psi inverse, if you take its closure with respect to whatever topology you have, you get the entire group G. Okay? So this is a notion that was introduced by, oh man, I forget the names again. Benjamin Weiss, Glasner and Weiss. So 2 ergodic theorists, I think both of them are at Tel Aviv. And this is something that comes up in their works a lot. And examples of this, I'll give you one example. So there are lots of examples that they give in their papers. But one example for us that would be interesting is if you take the homeomorphisms, orientation-preserving homeomorphisms of a 2-sphere. This is Rochlin, so it has a dense conjugacy class. Now, independently of the work of Glasner and Weiss, Béguin, Crovisier, and Leroux, so these are 3 surface dynamics guys. Leroux is the same Leroux with whom I collaborate. And all of these guys are based in Paris. They asked, so they had actually different reasons than what Glasner and Weiss had in mind. They asked if is the group of Hamiltonian homeomorphisms. Actually, they asked it only for the sphere, but the question makes sense for any M. Is this Rochlin? Okay? And so it turns out that symplectic rigidity kind of forces this. The symplectic groups turn out to be not Rochlin. And this is kind of an immediate consequence of the fact that gamma is C0 continuous. So suppose, for the following reason, so the answer is no. And here is the proof. So let's remember that we have got this gamma from defined on now ham bar of M to the real line. Gamma is well known to be a conjugation invariant norm. That's one of its key properties. So gamma on the conjugacy class of theta is constant. It's just conjugation invariant. Now, if conjugacy class of theta is dense, by continuity it's constant on the closure. So if you had a dense conjugacy class, gamma would be constant on the entire group of Hamiltonian diffeomorphisms, for example. But it's known that gamma is non-trivial. That's one of the, that's the energy capacity inequality, one of the deepest results in our field. So, So we see that, okay, ham bar of n is not roughly. So that's another application to dynamics. And I hope, okay, good. I haven't gone much over time. So I'll stop here. Thanks.
So questions for Sobhan or comments?